Our universe is vast, stretching farther than our minds can truly comprehend, with billions of galaxies scattered across the cosmic ocean. It is filled with mysteries that have eluded us for millennia, secrets hidden in the darkness between the stars, waiting to be uncovered. For generations we've gazed at the stars, our curiosity driving us to build ever more powerful telescopes. Each new instrument has peeled back another layer of the cosmos, revealing wonders we never imagined. But to see the very first stars and galaxies, to peer through thick clouds of cosmic dust and glimpse the universe's earliest moments, we needed a new kind of eye, one that could look deeper and further than ever before. That eye is the James Webb Space Telescope, or JWST. JWST is more than just a telescope, it's a time machine, engineered to see the universe in infrared light. This allows it to capture ancient light that has traveled billions of years to reach us. Light that is invisible to our eyes but holds the secrets of the early universe. Its golden mirror, spanning over 6 meters across, is made up of 18 hexagonal segments. This massive surface collects the faintest glimmers of light from the most distant and ancient objects in the cosmos, letting us look further back in time than ever before. Orbiting 1,000,000 miles from Earth, far beyond the reach of our planet's warmth and interference, JWST remains cold and undisturbed. This perfect isolation is essential for detecting the faint heat signals from the earliest stars and galaxies. With its powerful infrared vision, JWST can pierce through dense clouds of gas and dust, cosmic nurseries where new stars and planets are born. It reveals the hidden processes that shape solar systems and galaxies. JWST can also study the atmospheres of distant exoplanets, analyzing their chemical makeup and searching for potential signs of life. It brings us closer to answering the age-old question, are we alone in the universe? This is a revolutionary leap in our quest to understand where we come from, how the universe began, and whether life exists beyond our world. Every image and data point from JWST has the potential to rewrite our understanding of the universe, challenging what we thought we knew and inspiring new questions. It's our silent observer in the dark, patiently gathering stories from distant worlds and forgotten epochs, sending them back across the void for us to study and marvel at. JWST is not just a triumph of technology, it's a symbol of human curiosity and ingenuity, a new chapter in humanity's ongoing exploration of the cosmos. It is truly our window to the origins of everything, inviting us to look back in time and discover the story of our universe. Far from the sun, Neptune orbits in the cold, dark reaches of our solar system. This ice giant's deep blue color comes from methane gas, but beneath that calm exterior lies chaos. Neptune's winds are the fastest in the solar system, with storms that dwarf Earth. It radiates more than twice the energy it receives from the sun, hinting at a mysterious internal heat source. Its interior is a strange mix of water, ammonia, and methane ices, possibly even diamond rain. Before JWST, our best views came from Voyager 2 and Hubble, leaving Neptune shrouded in mystery. Its faint rings, icy moons, and dynamic atmosphere were hard to study from afar. JWST's infrared vision changed everything, offering a clear, detailed look at Neptune's weather, rings, and atmosphere. For the first time we could truly observe this distant blue world. Neptune, long enigmatic, was finally ready for its close-up. And then, something extraordinary happened. On June 21, 2025, astronomers around the world turned their attention to Neptune, using the powerful James Webb Space Telescope to study the distant planet's mysterious atmosphere. They were tracking the movement of its icy clouds and measuring subtle changes in temperature, hoping to unlock secrets about this remote giant. Suddenly, in the midst of their observations, JWST detected a brilliant, unexpected flash of infrared light erupting in Neptune's northern hemisphere, a burst so intense and sudden that it overwhelmed and saturated the telescope's sensitive sensors, leaving astronomers momentarily stunned. This was no ordinary storm or atmospheric disturbance. The data revealed the unmistakable signature of a massive high-speed impact event. Something enormous had just slammed into Neptune, leaving a clear and dramatic mark. News of the discovery spread like wildfire. Within hours, astronomers and observatories worldwide were focused on the data streaming in, eager to analyze every detail of this rare cosmic event. For the first time, humanity had a front-row seat to a real-time cosmic collision unfolding before our eyes, a phenomenon rarely witnessed in the vastness of space. The impactor, likely a massive asteroid or comet several kilometers wide, struck Neptune at a mind-boggling speed, tens of thousands of kilometers per hour, releasing energy equivalent to millions of nuclear bombs. On Earth, such an event would spell disaster on a global scale. But on Neptune, a planet far larger and more resilient, it was a dramatic yet survivable wound, a testament to the planet's immense scale and power. The planet's thick, swirling atmosphere shuddered and rippled, reacting instantly to the colossal blow. Shockwaves raced through the clouds, creating turbulence and chaos in the upper layers. For scientists, this was an unprecedented opportunity, a chance to witness, in real time, the immediate aftermath of a major impact on an ice giant, and to study how such a planet responds to cosmic violence. It was a stark and humbling reminder that our solar system is not a static place, but a dynamic and sometimes violent arena, where planets and celestial bodies are constantly shaped by powerful forces. We had just watched a celestial wanderer, a rogue asteroid or comet, end its journey in a spectacular blaze, consumed by Neptune's vast atmosphere in a final, fiery display. The sheer scale of the event was staggering, and the implications for our understanding of planetary science were profound. It was a moment that would be studied for years to come. Nature had just conducted a grand planetary experiment before our very eyes, and for a brief, unforgettable moment, we were privileged to watch it unfold. Confirming the flash was an impact required swift, careful analysis. Teams of astronomers around the world immediately began poring over the data, comparing notes and scrutinizing every frame. The initial reports were met with excitement and skepticism. After all, Neptune is a dynamic world and false alarms are not uncommon. But this event was different. The sudden, intense burst of thermal energy matched models of a high-speed object slamming into a planet. The energy released was far greater than anything produced by Neptune's own weather systems, and the infrared signature was unmistakable. Unlike storms or lightning, the event was brief, bright, and sharply localized. A cosmic muzzle flash. It lasted only seconds, but its intensity was off the charts, far brighter than any known atmospheric phenomenon on Neptune. JWST spectrographs revealed silicates, metals, water ice, and organic molecules, materials not found in Neptune's upper atmosphere but common in comets and asteroids. This chemical cocktail was a telltale sign that something alien to Neptune had arrived with tremendous force. The impact vaporized these materials, throwing them high into the stratosphere and leaving a chemical fingerprint. Plumes of debris rose above the clouds, dispersing into Neptune's winds and settling into new patterns that could be tracked for days. JWST images soon showed a dark, evolving scar in Neptune's blue clouds, a physical change, not a shadow. This mark grew and shifted, evidence of the planet's powerful winds stretching and distorting the impact site. This was similar to the scars left on Jupiter by comet Shoemaker-Levy 9. Those marks too were unmistakable signs of a violent cosmic collision, and now, Neptune bore its own. The impact site remained warmer than its surroundings, a lingering thermal echo. This heat signature persisted for days, slowly fading as Neptune's atmosphere worked to erase the evidence. JWST's ability to map these temperature differences was crucial. By monitoring the heat, scientists could estimate the size and energy of the impactor, and even model how the debris spread through Neptune's atmosphere. By tracking the heat and debris, scientists watched Neptune's winds stretch the impact site into a long, dark streak. This evolving scar told the story of the planet's dynamic weather and the force of the collision. All evidence, the flash, chemical debris, dark scar, and lingering heat, painted a clear picture. Neptune had been struck, and struck hard. The data left no room for doubt. This was a true cosmic impact witnessed in real time. The universe had delivered a direct hit, and JWST had captured it all. Thanks to this remarkable telescope, we were able to witness and understand a rare, violent event unfolding on a distant world. The collision unleashed chaos in Neptune's atmosphere. A shockwave radiated from the impact, heating and compressing the gases, glowing in infrared. The vaporized impactor left a plume of superheated gas and debris, forming a thick, dark haze high above the clouds. This sooty material created a visible scar, stark against Neptune's blue. The energy triggered violent weather, updrafts, vortices, and storms swirling around the impact site. Neptune's jet streams stretched the debris into a long, dark streak. For scientists, it was a rare chance to observe deep planetary processes revealed by a cosmic visitor. As days passed, Neptune's dark scar was swept up by fierce winds, stretching into a band around the planet. The impact's heat broke apart methane, creating new hydrocarbons like ethane and acetylene, detected by JWST. Water vapor from the impactor was injected into the stratosphere, altering Neptune's chemistry. The collision created a temperature imbalance. sparking new weather systems and convective patterns. Scientists tracked the formation of vortices and waves rippling away from the impact zone. This event became a real-time laboratory for studying atmospheric dynamics. How long would the debris linger? Would a new great dark spot form? The impact's effects would ripple through Neptune's skies for years to come. This collision was more than a spectacle. It was a scientific goldmine. The impact acted like a seismic event, sending shockwaves deep into Neptune's interior. By studying these waves, scientists could map the planet's hidden layers for the first time. The debris revealed the impactor's composition. Was it a rocky asteroid or an icy comet? This helps us understand the building blocks of our solar system. The event also tested and refined our models of planetary impacts using real data from an ice giant. JWST's observations will shape our understanding of planetary formation and evolution for years to come. The Neptune impact shows why we explore. The universe is dynamic, unpredictable, and full of surprises. JWST's success in capturing this event marks a new era of real-time planetary science. Future missions will be designed to react to sudden events and study their aftermath. The case for a dedicated Neptune orbiter is stronger than ever. For us on Earth, this event is a humbling reminder of our place in the cosmos. Each discovery deepens our understanding and sparks new questions. The journey of exploration is endless, and JWST will continue its silent watch. The Neptune collision is not an endpoint but a brilliant signpost on our voyage into the universe.